In this video, we will continue with calculating delta G and get practice utilizing this equation. Sum of the products is equal to sum of the reactants. So the sign is very important. This delta G stands for Gibbs free energy. If the reaction, when you do this math, is negative, the reaction is what is known as exergonic. It means it will release free energy. This is the energy that is useful, and it can actually be utilized to do work, whereas heat cannot be utilized. Entropy also is a measurement of order and disorder. Temperature can also help facilitate a reaction. But this is the final judge, and it's delta G, known as Gibbs free energy. This equation is for 1 mole. So when we look at a problem like this, we realize that, for example, sum of the products minus sum of the reactants. For this one, we have 2 moles, so we got to multiply the value we get by 2. So let's go ahead and do this problem here. Sum of the products, so we have MgO, magnesium oxide. We look that up in the table in the back of our book, or we look it up on any sheet here. So notice the thermodynamic data has delta H enthalpy, delta G free energy, and entropy. All of these are standard state, symbolized by that not symbol. So MgO, magnesium, is right here. Okay, make sure you have the right state here. It's going to be minus 569.6. We got to multiply this by 2. 2 times minus 569.43. Okay, I'm going to add the units later. Sum of the products minus sum of the reactants. Oxygen is 0, okay, because that's baseline, natural abundance. And then magnesium solid. Let's see here, we have magnesium gas. So that's not going to do it. We want magnesium solid. My inkling is that it's going to be 0 because that is natural abundance for magnesium, baseline. That is the default. And yes, I was right. So magnesium has a delta G of 0. Okay, so this is the delta G right here, and for magnesium, that's 0. So it's going to be 0 kilojoules per mole here. So the final answer for this problem is 2 times 569.43, and that's minus 1138.86 kilojoules per mole. Okay, the minus sign tells you that this reaction is a go. You take magnesium solid and bubble in oxygen gas, you'll immediately get this magnesium oxide precipitate. The energy that is released is minus 1138.86 kilojoules per mole. That released energy can really be utilized to do some power, some other reaction, maybe a reaction that's endergonic. All right, moving on to part B here. Okay, looking these values up and making sure you're doing the right math. We got 2 SO2 plus oxygen, that's going to be 0. Going to sulfur trioxide. Okay, so we got 2 moles of this, 2 moles of that. So 2 moles of SO3 gas, looking that up. So SO3 gas has a delta G here of minus 371.06. SO3 gas, make sure you're reading the right one here. 2 times 3 minus 371.06. times this minus sum of the products, this oxygen is 0, plus 2 times SO2 gas. And SO2 gas, let's see, we got to look this up here. SO2 gas minus 300.19. Make sure you read the right one. We're calculating delta G here, not delta H nor delta S. It's delta G minus 300.19. 2 times minus 371.06 minus 600.38 kJ per mole, kilojoules per mole. So 2 times this, minus into minus is plus. So at the end, the reaction will be minus 2 times 371.06 minus into minus plus a 600.38. On my calculator, I'm getting an answer of still minus 141.74 kilojoules per mole. Okay, again, we call this an exergonic reaction. We expect this reaction to proceed in the forward direction and generate products by virtue of the minus sign. Here at standard state, 25 degrees C, Under 1 atmosphere of pressure, because these are gases, this reaction would be exergonic. Part C of this problem looks like we have another combustion reaction where we produce CO2 and water, and this is going to be 0. We got to find CO2 in our table multiplied by 4, water, liquid, in our table multiplied by 6, and C2H6, I think that is ethane, the alkane ethane. We got to find that value and multiply it by 2. So first let's do CO2 and multiply it by 4. So looking at this in our table, I am seeing at our table here, I am getting CO2 gas, meaning being minus 394.36 times 4 because we have 4 of these. Okay, make sure you use water as a liquid. Okay, not water gas or not water solid, because this is a common mistake people make, not having the right state. And here we're going to use the state of water liquid, which is minus 237.13 for our delta G. We multiply that by 6 because there's 6 of those. Units are kilojoules per mole, so we'll do that at the end. Oxygen is 7 times a 0. We can look it up and we'll see a 0 there. Plus 2 times C2H6. That's called ethane. Methane, ethane, propane, butane, all of those alkanes. Hydrocarbons, hopefully you remember that from our section on intermolecular forces, and the hydrocarbons are also known as the alkanes. So that's an organic substance. So C2H6 here, ethane, and we're going to look up the delta G of minus 32.82. And we multiply that by 2. So 2 times minus 32.82. And the final answer is going to be in kilojoules per mole. I'll just do the math and put our final units here. Doing this on my calculator, I'm getting about minus 2,931 kilojoules per mole. Again, combustion reactions, no surprise. The negative sign tells us it's exergonic, and this reaction favors the products. It would happen on its own devices in standard state. Remember, standard state conditions, delta G naught, 25 degrees C, 1 atmosphere if you're talking about gases, 1 molar if you're talking about solutions, solute plus solvent.